Okay, so in terms of the calculus course that I'm involved in next semester, it's not just any 270 course. It's the one specific SLN that I posted on Blackboard announcements. I'm having trouble getting that up right now. But there's only one section of 270 that is what I'm going to be involved with. It's going to be similar to this class. So it's not just any 270 course. If you want to try to get in that, you can just try the normal way. I guess there's some students have been able just to get in without jumping through any other hoops. Okay? So try that first. If you can't get in, it says reserved or you're having difficulty. Hold on, you guys can't talk over that. If you're having difficulty, you can't get in, then contact me and I'll let you know what you need to do. Question?
Here's the only one that's the 10:30 to
Yep, 10:30, Monday, Wednesday, Friday, MAT 270. And the SLN, the line number is in the Blackboard announcements. So it's only that one section. If you get a different section of 270, it'll be more similar to the traditional calculus course, like 265. Okay. So, and I'm not involved in that. I'm only involved in the one section. Okay. So if you're having issues getting into, if you want to get in, you're having trouble, just talk to me. But try to get in normally. Okay. So are we collecting homework? Collecting homework. And while you're doing that, I think you had a problem about barks, right? So let's make this circle down here the bark circle. So if you can just, as you're handing it in, if you can just pay attention still. So we're going to make the lower right circle here the bark circle. And how many barks in a full rotation? 240. Okay, so what about 175 barks? So consider an openness of 175 barks, and we want to find the equivalent number of degrees and radians. Do I have everyone's attention? I hear continued talking. Okay, we're starting class. All right, so ready to start. Okay, 175 barks. So we want to find the equivalent number of degrees and radians. So before we do that, let's just talk about what is an angle of 175 barks, just without doing any calculations. How much openness is that? Can you make an estimate as to how much openness 175 barks is? Okay, if there's 240 total, so maybe talk for a second with the person next to you. If I were to grab onto the terminal side here, where would I stop? Where would I stop here, okay? If I'm doing 175 barks. Go. Talk about that for a second. How many barks would be what we call a straight angle, or half of a circle? How many barks would that be? 20. Okay. How many barks would be 3/4 of a circle? Was it? 60 more, right? So you're going to take half of 120 more. So what is it? 180. So what about 175 barks? A little bit less, right? So maybe like that. Okay. So this amount of openness right here is our 175 barks. So if we want to make a conversion, what do we do first? We want to convert this to any other type of angle measure. What do we want to do first?
Well, since maybe the 240, you get 175, 240, set that equal to
So what did you say first? Did you say 175 divided by 240?
Yes.
Okay, what does that represent, that value?
Percent of the circle.
Right, the fraction of the circle that is equivalent to this amount of openness, 175 barks. So, and then where should I put the terminal side of this angle?
About
Where should I put it?
the same spot.
Same spot. That's the whole point, is we're not changing the amount of openness, we're just using different systems of measuring it, all right? So it's the same amount of openness. So what percent of the circle is this? You said?
155.
Yeah, and we can you can find a decimal approximation to that, or you could just leave that fraction. That's just as valid of a number in that form as some decimal approximation that you would find, okay? So 175 barks is this fraction of a circle. So then, how do we get degrees if it's this fraction of a circle? Yeah, gee. Okay, and what effect does that have? So you want to take that and multiply it by 360, and what effect does that have? What is that doing? So you want to take that 175 over 240. Right. Yeah, so we want the same fraction of 360 that 175 is of 240. So we take that fraction, that percent of 360, and we'll get the equivalent number of degrees. Where am I going to put the terminal side? Same place. Openness doesn't change. All right, let's get it. Now let's get an approximation, because degrees are something we can kind of latch onto here. 262.5 degrees is equivalent to 175 barks. Okay? Where are we going to go to if we want radians? What are we going to do to get radians then?
Take that same fraction of 175 over 240
Take that same fraction.
and multiply it by the 2 times pi.
Because 2 pi is
The full measure of a circle.
6.28 radius lengths, about 6.28, or exactly 2 pi radius lengths give us a full circle, and we know those radius lengths is how we get our openness in radians. Okay? And so we're going to take that same fraction of 2 pi. So let's just let's estimate our radius lengths here. So number 1 is about, we saw number 1 was about here, right? Number 2, about here. Number 3, before or after halfway? Before or after? A lot before? Just a little bit before, because halfway is 3.14 about, or exactly pi radius lengths, takes us halfway around the circle. And so then 4 is about here, and 5 is down here. So I don't know. What'd you get? All right, so I'm shifted too far. So I guess it's more like this. So this is 4, and this is 5. And so for radians, it's a little bit more than 4.5. If you take the same fraction, 175, we want that percent, or that fraction of 2 pi. And you said it's 4.58? 4.58, right there. A little bit more than halfway from 4 to 5. Okay, so then with this system of always going to percent of the circle, and from percent of the circle you can do anything, it works because what a great advantage to it is if you're given a new system that you've never heard of before, like barks or oinkers or something else, then you can always just convert it to percent of the circle and get whatever you need. Okay? And you never have to memorize any formula. All you have to know is, for a given system, what is a full rotation? 240 barks, 360 degrees, 2 pi radians.
What's the full thing for
Gradients?
400?
I think it is 400. Is it 400? And there may be others too. Okay, any questions on converting? All right. And then, so let's just, hold on. So if you open up to page, where you left off in the homework on that investigation, what page is that? 265. So in 265 it says there's a fan, and there's a bug sitting on the end of the fan blade, and it's rotating counterclockwise, and the fan blade has a radius of 2.6 feet. And it says that it starts at the 3 o'clock position, and the fan starts at 3 o'clock position. That's where the bug starts, and then the fan begins rotating counterclockwise, just like our conventional angle that we've talked about. Okay? So I want you to answer. You got the visual here. The radius is 2.67. Or sorry, 2.6 feet is the radius of the fan blade. And so I want you to answer those questions on page 265. Go. That's all review. It should be review. Just now we're in context. We're given a situation. Okay? So this. So try to really work on the meanings of things and the reasons rather than just plugging into a formula. Actually, I just want you to do 5, A and B, and 6. Do 5, A and B, and 6. Okay. If the bug goes 5.2 feet, how many radians were swept out? So if the radius is 2.6 feet and the bug travels an arc length of 5.2, why 2 radians, Faisal? Why does that work? What are you doing by doing that calculation?
Because the radius is 2.6.
Okay.
Travel twice.
Right. Good. So the arc length 5.2, we want to know how many radius lengths that is. If we want to know how many radians of arc that is, of arc that is, then we want to know how many radius lengths the arc is. So if we got 5.2 feet, to get the number of radius lengths, we're going to divide up that arc length into the length of each radius, which gives us 2 radius lengths. And that's what I'm showing in that picture there. 2 radius lengths are cut off by the rays. Therefore, angle of 2 radians. Okay, so what about 11.7 feet? So 11.7 feet, wherever that, somewhere down here. How'd you get that?
Divided 11.7 by 2.6.
And why does it work?
Because the fraction of circumference divided by the radius is the openness of radius.
Okay, that's the number of feet. 11.6 is feet, right?
Yeah.
So it's not a fraction of the circumference. You said that was 4.5?
So the distance traveled in a circle. So
Okay.
defines the number of radiuses that are in the arc.
He said it defines the number of radiuses that are in that arc length. If the total arc length is 11.7 and each radius is 2.6, then we're finding the total number of radius lengths that are in that arc length, which ends up being right about there. Which was almost exactly the same as what we had earlier with the 175 barks, because it was 4.58. Remember that? It's 4.58 radians. Okay, so this arc length is 11.7 feet, and that's 4.5 of 2.6 feet. So that's our angle measured in radians. Okay, then it says we're going to go, in number 6, we're going to go 0.765 radians. How far does the bug travel? So here we're going to go right about there. So this is 0.765 radians. How far did the bug travel when the fan turned 0.765 radians? How far did the bug travel?
1.98 feet.
How'd you get that?
I multiplied 0.765 with the radius, which is 0.6.
And what, in effect, are you doing by that calculation? What does that calculation do?
We get 0.7 of the radius.
0.765 of the radius. Yeah, so we want, if this is 0.765 radius lengths, so that's what we want of the radius in feet. And you got 1.98 or 1.99. Okay, so you have to be really comfortable making this quick transition between the openness in radians and what? The rays cut off that same number of radius lengths, right? That openness in radians comes from the number of radius lengths cut off by the rays of the angle. And so when you're doing these problems, you should always be thinking about that. Thinking about what radians is. It's the number of radius lengths cut off by the rays of the angle. Questions on these examples? Okay, so now we're interested in, so we got the bugs moving around here, and what we're interested in now is pinpointing the location of the bug. So pinpointing the location of the bug. So given an angle swept counterclockwise from the 3 o'clock position, what's the location of the bug? So what quantity? What quantity or quantities can we monitor that will tell us the location of the bug? So what can we think about that was, so given a certain angle, say Say right here, okay? So there's a certain angle that the bug's gone through. Do you see that that determines a unique location? There's a, yeah, so given some angle here, called theta, that will determine some unique location of the bug. So what quantity or quantities will give us that location? Any ideas? What quantity or quantities will help us to determine this precise location of the bug after a rotation of this many radians? Nas? The radius. Okay. Does the radius change? Okay, so the radius stays the same. So, okay, so the radius might help us. We'll make a list here. So the radius. What else? Other hands. Aiden. What's that? And so what do you mean by that? So exactly what quantity are you talking about? When you say y, what distance, right? Yeah, but there's a dozen different distances we could talk about here. Remember the first week of class? You got to be specific. We could say
On the x-axis and y-axis.
right, and what distances do those measure? Yeah. Arc length is a different one. Okay. Other ideas? Yeah. Circumference of the circle. Okay. Trying to get the location of the bug. So let's go back to this one. He was onto something, but we want to be specific. So what distance are we talking about? Like, are we talking about the distance from straight line distance from the starting point? That's not very convenient, right? So that changes as the angle changes. Doesn't really help us get the location of the bug. Distance from the origin. What's this distance from? Distance from the center of the circle. Let me give you. That'll always be the radius, won't it? So look, we want to talk about this thing called the horizontal diameter of the fan. To start with. So this is the horizontal diameter of the fan. So in tracking its location, what could we measure relative to the horizontal diameter? So this goes back to distance. What distance could we measure relative to the horizontal diameter? Yeah. The arc length? The arc length doesn't have anything to do with the horizontal diameter. Yeah, so we got arc length, but what about relative to the horizontal diameter? What's that? Not a vertical diameter, right? So vertical diameter would be here. But what distance? So you're on the right track. What's that? Radians is that's our given angle. So now we're saying what distance relative to the horizontal diameter will help us get the position of the bug. Time is not a distance. Let me give you another visual here. Say, what's that? Yeah, so it's we're going to call it the horizontal diameter. The distance from the bug, the vertical distance to the horizontal diameter. See, I'm showing that in red. Okay? So we'll call that the vertical distance, and I'm going to say above the horizontal diameter. Can I say above even though half the time the bug is below? Still okay to say above? So what would it mean? Yeah, so when the bug is below the horizontal diameter, it'll be the negative value of that, it'll be the opposite of the distance. So we'll have negative values for this quantity when the bug is below and positive values when it's above. Okay? And so we're going to do that in feet. So what's the greatest value that that quantity attains? The vertical distance above the horizontal diameter in feet. And where does it attain that? At what angle? So at the very top of the fan, the top of the circle, is where the bug attains the highest value of this quantity, and that's 2.6 feet. And what's the very lowest value of this quantity? 0? Negative 2.6 at the bottom, okay? So then what else could we track? There's more to the story. What else could we track? Yeah, so then we could do horizontal distance from the vertical diameter. And when we want to use specific, horizontal distance to the right of the vertical diameter. So we can show that as well. Show them both at the same time. Okay, so these two quantities, the horizontal distance above the vertical distance above the horizontal diameter, and the horizontal distance to the right of the vertical diameter, given an angle, will pinpoint a specific location of the bug. Okay, so today we're going to focus on this one. Okay, so we're actually just kind of creating a function here. The input is the angle, and then the output, we're going to focus on the output of this vertical distance above the horizontal diameter. So I'll turn this other one off. So the input is the current angle, and the output is the vertical distance above the horizontal diameter. We're going to kind of investigate that, the covariation of those two quantities. Why? Because our goal is knowing the location of the bug at any given moment. Knowing the location of the bug. Eventually then we'll talk about both. All right. So we've got a similar deal here. How do we talk about the covariation of two quantities? Does anybody remember how we investigate? So two quantities are changing together. Does anybody remember how we go about understanding how they covary or how they vary together? What do we start with? So we've got input. Our input is, let's write this out. Input is angle, right? Is that a good descriptive quantity? No, there's a dozen angles we could define in the context of this fan. Which angle are we talking about? Remember, when we define quantities, got to be specific, or else we don't know which angle we're talking about. So which angle is it? Give me one aspect of it. What's that? Okay, we need the units, so we'll do this angle in radians. Angle in radians. Does that tell us what angle we're talking about? No, still, there's a dozen angles in radians that we could define. Jonathan? Okay, angle from the 3 o'clock position. That's one aspect that we need. What else do we need to know? Yeah, Michael? Okay, so the vertex, right, is at the center of the circle. That's true. What else do we need to know about the angle? Yeah. That's what we're measuring. But we need to describe which angle, what angle is it in terms of terminal, initial side, how it's swept open, and terminal side. Is there only one angle we can do from the 3 o'clock position? Scott, were you going to say something?
I'm not really sure. The angle of the terminal ray from the initial side.
Right, and is there only one way we could do that from the 3 o'clock position? We need to specify what direction is a positive opening angle. Yeah, swept counterclockwise. So we got the angle swept counterclockwise to the 3 o'clock position in radians. Our output is that's what we said before. Our output's going to be the vertical distance above the horizontal diameter in feet. Sorry, I'm a little messy today. I don't know what's going on. Vertical distance above horizontal diameter in feet. Not a banner day for legibility, but you can make it in your notes. Nice and neat. Okay? That's our input and output. How do we investigate? What do we do first when we want to investigate how these two things covary together? Remember the bottle problems and the walk? What do we do first? Remember? Yeah.
Measure equal changes in the x.
In the input or output?
In the input.
He wants equal changes in the input. What do you think? Start with equal changes in input. That's it, right? We want equal and usually small changes in input. Equal and small changes in input, and then we investigate. We got 3 questions that we ask about the output. Okay, so here I've set it up. So I've got equal changes in the input, which is our angle. So that there are 4 per quadrant. So tell me figure out what is my change in input that we're going to be looking at. What change in input will we be looking at if we do 4 slices or 4 changes per quadrant? What will it be? We'll be looking at what changes in input. Well, it all starts with exactly halfway around the circle. Halfway around the circle is pi. So a quarter of the circle is pi over 2. A quarter of the circle is half of pi. Take half of that again. So 1/8 of a circle. Pi over 4. So therefore our increment's going to be pi over 8. We're going to go by pi over 8s, okay? So we're going to let the angle increase by pi over 8 each time. And then we're going to ask some questions. Does anybody remember what questions we're going to ask? What's the first question we ask? Any volunteers? Yeah.
For each equal change in x, what is the change in 1?
So yeah, is it positive or negative, right? So we look at question 1 is how does the output increase or decrease? So for a change in input, what does the output do? Does it go up? Does it stay the same, or does it go down? Okay, that's our first question. Second question was, what do the changes do? So we're comparing the current change in output with the previous change in output. And to help us with that, we ask, are the changes becoming more positive, more or less positive or negative? And that helps us determine how the changes are changing. Okay, so I have what I want you to do is, question 1 is analyzing the output quantity. Is it increasing or decreasing? Question 2 is analyzing changes in that quantity. So in my animation here, where should you look to answer question number 1, what the output quantity of vertical distance is doing, and where should you look to investigate changes in the output quantity, okay? So just take a moment and talk amongst yourself. Where should we look to see how the output quantity is changing, the vertical distance above the horizontal diameter? And where should we look to see how the changes are changing? Go. Confirm that with the person next to you. Okay, what are you going to look at to see if the output, the vertical distance, is where you're going to focus your attention to answer that first question? So what aid have I given you for that right there? What do you think? Does that help you? So what is that helping you with? The dots. Don't the dots show you the changes? Okay, and so what's showing you the actual quantity of the height? The red line, okay? So we're going to look at the red line to talk about the height. That's our height above vertical diameter, horizontal diameter. And the dots are going to help us analyze the changes, okay? So let's just look at that first. Let's see this here. So we're going to do one full rotation, which is what in radians? 2 pi. So halfway around the circle is? Top of the circle? Bottom of the circle? 1.5 pi, right? Okay, so let's talk about the first quarter of the circle. That vertical height goes from what to what? Just the vertical height now. So the vertical distance above the horizontal diameter starts at what and ends at what value? So as the angle goes from 0 to pi over 2, what does the vertical distance do? It goes from 0 to? I'm hearing conflicting answers for where it goes to. What's the final value of the vertical distance above the horizontal diameter? What are our units for this output? Vertical distance and what? And we said in feet, right? We said in feet. So what is this final value of the output? 2.6 feet, right? So it's going to start here. At an angle of 0, it's going to the vertical distance will be 0, and at pi over 2, that vertical distance will be 2.6 feet, okay? So now we can look at the changes. So in the first pi over 8 angle, what happens to the vertical distance? Increase or decrease? Increase. Okay, next pi over 8. What happens to the vertical distance? Increases again. Now we compare that current change with the previous change. What? Is it more or less positive or negative, that change, than the one before? Less positive. Our vertical distance is increasing, but the amount of change is less than the one before. Okay, third change. Vertical distance, increase or decrease? Increase. The amount of increase, more or less than the previous? Less. Okay? So, are the changes increasing or decreasing? The changes. So the vertical distance is increasing from 0 to 2.6, but the changes are decreasing. The changes are decreasing, and so therefore the rate of change is decreasing. Okay? So we can mark this off. Pi over 4, pi over 8. So in exactly 4 equal ticks of angle there. And so at pi over 8, this is our vertical distance. You told me the next change was how compared to that one? Next change. Less of a change, right? Less of a change. So that at pi over 4, the height is now this. Next pi over 8. How does that change compare to the previous? Less of a change. So the changes are decreasing, so the rate of change is decreasing, meaning the graph is concave down. I was doing good until that last part. Just paying attention. A little OCD today. It's okay. There we go. Slightly, whatever. All right, you get the point. So what I want you to do is, second quadrant. You're going to go through the same 2 questions. What does the vertical distance do? And what, think about it and talk it out among yourselves. And then, what are the changes doing in that second quadrant? So, what does the vertical distance do? And what do those changes do? And so then what does the rate of change do in the second quadrant? I'm going to finish taking roll, okay? Talk to the person next to you. Second quadrant. Distance do in the second quadrant? Increase, decrease, or stay the same? It decreases. That's just the red bar, right? The red line is getting shorter, or the bug is going down, right? The bug is going down. Now the changes. Okay? So are the changes positive or negative changes? Are these changes positive or negative in the vertical distance? Okay, we should all be saying this in chorus. If, you know, is the change in the vertical distance positive or negative in this quadrant? Negative. Okay, negative. Are those becoming more negative or less negative? Right, they're becoming more negative. So are these changes decreasing or increasing? Decreasing. Okay? All right, hold on. So this is what we all missed, a lot of us missed on the test, and it's sticky, okay? Yes, the amount of change, total amount of change is getting greater, but because these changes are negative, they're getting larger negative. That means those are decreasing changes, okay? And so then what about the rate of change? Decreasing rate of change. Okay? Decreasing rate of change, because the changes are negative, and getting more negative. Negative changes getting more negative are decreasing changes. Okay, I'm going to post Friday's homework shortly. See you Wednesday.